Good morning to everyone. Yeah, I hope all of you are, those who are in Tamil Nadu or Andhra region are staying safe. Yeah, today we are going to get
Your
a lot
voice
of.
is low, sir.
Sorry?
Your voice is actually very feeble.
Feeble, is it? Okay. Is it any better now?
Yes, sir.
Or is it the
Yes,
same?
sir. Yes, sir.
Okay. Okay, good. Okay, so I hope those who are in the East Coast are staying safe, particularly Andhra Pradesh and Tamil Nadu. Okay. Okay, so welcome to lecture number 35. We were looking at shortest path algorithms. Particularly in the last lecture, we looked at an algorithm, a generic algorithm as we call it, by Ford. And in fact, it's attributed to Ford, but there are several researchers who came up with same algorithm around the same time. So the idea is, as long as there is a tense edge, we relax. So this is the relaxation step. So this is the tenseness condition. Okay, so what we do is we have tentative distances for each of the vertex. So as we have seen it, we initialize, except from S, all other vertex, the initial tentative distance is infinity. And so for every tense edge, you just apply this relax step. This is a this is initialization. This is a relaxed step. Okay, so if the edge is tense, then what you do is you update the distance of the vertex V, that is the endpoint of the edge UV, with the distance of U plus weight of UV, and you accordingly update the partial shortest path tree that we are building with the predecessor of V as U. Okay, here is the generic algorithm. So for every edge, if edge is tense, then we apply relax. Okay, so just to expand, relax is basically distance of V is distance of U plus weight of UV. Predecessor of V is U. Okay, so this is how it looks like. So we didn't prove the correctness of Ford's algorithm. We just stated some conditions which would give us correctness. In today's lecture, we will be looking at an implementation of this. Yeah, so this is what is required for correctnness. So assuming that there is no negative weight cycle, so we inductively prove, or we can inductively prove that either distance of a vertex is infinity or a length of some simple path from S to V. And further, if there is no tense edge, then we'll argue that the predecessor relation in fact represents the shortest path, and distance V is the length of that shortest path. Okay, we'll skip the details. We'll talk about implementation. So like I said yesterday, now, so Ford's algorithm is kind of generic algorithm. It does not tell you how to choose edges and so on. It's up to the implementer. Okay, and how many iterations it will go. We can of course argue that after a finite number of iterations or finite number of steps of applying relax, the algorithm will terminate. Okay, but yeah, so what would be the naive implementation? So we don't really know how many iterations are required first hand. So that way the implementation details are not clear. So what subsequent researchers did were essentially implementation of this generic algorithm. Okay, see, it all matters how do you choose these edges for relaxation, right? So you can use BFS order or DFS order. Okay, so the corresponding algorithms are BFS shortest path or DFS shortest path. Unfortunately, these choices won't work right away. They work only on special graphs. Particularly BFS works on unweighted graphs. There is no edge weight at all. Well, then it's not interesting because we wanted edge weights. And DFS works when there is a guarantee that the graph is acyclic, directed acyclic, in the sense that there is no directed cycle. Though graph as such, if you remove the directions, might have cycles. Okay. Two other prominent implementations, or in fact celebrated implementations, are Dijkstra and Bellman-Ford. There are lots of other implementations too, but these are the ones which are taught very often. Okay, and also fairly efficient. Particularly Dijkstra is fairly efficient. So Dijkstra is essentially using priority queues, and the relaxation is applied based on extract min from the priority queue. And Bellman-Ford is slightly different in the sense that it does not do one edge at a time. So one epoch is, or one iteration is, for all edges you apply this relax step, and you repeat this certain number of times. So you can observe that if you repeat this for n minus 1 times, where n is a number of vertices, even then we are going to get correct paths, or we are going to be correct. Okay. So I'll start with Dijkstra's algorithm. So here the idea is the following. So what you do is, yeah. So we maintain a priority queue, storing vertices. Okay. So we initialize as in Ford's algorithm. Okay. So distance of S is 0 and predecessor of S is nil. And for every other vertex, distance is set to be infinity and predecessor is nil. We start with adding S to the priority queue. Okay. So now key is going to be the value of distance. Okay. So add S comma distance of S to priority queue. So it's like add, sorry. Add or insert S comma distances, which is 0. Okay. Now what you do is you repeat the steps until the queue is not empty. So every iteration you extract a vertex with minimum key from the queue. Now for that vertex, so you look at all outgoing edges. Okay. For each of the outgoing edge, you see if it is tens. So at the initial step, our u is going to be the start vertex S. Okay, so this is going to be u. So you look at all outgoing edges. So all of them will have key infinity and the corresponding vertices. Okay. Now you see if the edge is tens. Of course, all of them will be tens. So for each of them, you see if they are already in the queue. If it is in the queue, then apply decrease key. Else you insert that with the corresponding distance. Okay. So after relaxation, it will be weight of this edge, this edge, and so on. Okay. So that's essentially one step is. So once in one step, we'll be updating all outgoing edges of the vertex which was extracted from the queue. In the process, we will add elements to the queue. Okay. If the start vertex has no outgoing edge at all, then the queue will be empty. We'll stop immediately. But if there is at least one outgoing edge, then the queue will not be empty. We'll proceed further. Okay. So we'll argue that this can happen only a finite number of times. In fact, we'll argue that a vertex can enter the queue only at most once, not more than once. So hence the number of iterations here, so of this while loop will be at most the number of vertices times n times. And this of course is bounded by the degree of a vertex. Okay. So please stare at the algorithm and see if you have any questions before we go into an example and then prove the correctness. Okay. We'll be demonstrating it with an example. So this algorithm looks very similar to our Prim's algorithm, for example. But only thing is, in Prim's, you will be adding one edge at every point of time. Here, it's like you starting at S, you'll be flooding. Okay, so all neighbors of S will get their distance computed. Then all neighbors of these vertices will get their distance updated, and so on. In the process, in between, you find a shorter path, you will be applying relaxation. Okay, so that's the kind of intuition here. So only thing is, the order in which you choose these vertices is based on their computed distance so far. Okay, so shortest one so far, I mean, it may not be the distance at, but still whatever you have explored, the shortest one will be processed first. So that is the only prioritization. So for that matter, this algorithm is called greedy, because you are greedily choosing. The greediness here is a bit subtle, I mean, in the sense that it's, well, okay, you can say that it's not that subtle, but it's not like you're building a set right away. Okay, unlike MST or other algorithms. Okay, so here, so what you're doing is you're processing these vertices greedy. That's all. Okay, so you're not building a set as a solution. Okay, so that's why we cannot compare with the matroid paradigm. There is no matroid structure here, but still the choice is greedy. So we can call this as greedy. Okay. Yeah. So is there any
Sir,
question?
is the extract min choice greedy?
Yes. So that's what we are saying as greedy. So you're choosing vertices in some ordered fashion. Okay. And it's not exactly fitting our greedy definition of generic greedy algorithm and so on, because you're not building a set there. Okay.
Okay.
Yeah. Okay, good. So we'll
Hello,
demonstrate.
sir.
Yes. Yeah.
Can we go to the okay? So the relax UV includes changing the distance till
Yeah.
V and also including U as the predecessor to V.
Yes.
Both of them.
Yeah. So this is the relax step. So I've just highlighted here, right? So this is the relax step.
Okay. Okay.
These two. Yeah.
Okay, sir.
Okay, so we'll demonstrate this with the ready-made example from Jeff Erickson's book. Okay, so here this vertex is the start vertex. Okay, so this is the start vertex here. Okay, so S goes to the Q first. Okay, so distance of S is 0. So this is the initialization, and everyone else will have distance as infinity. Okay, so the edge labels are weights. Okay, the first iteration. So once you extract S from the priority queue, okay, so now you process it for every neighbor of S. Okay, so if you look at this step, so for all edges, UV, okay, U is S in the first step. Now you check if U is tens. So naturally, all of these edges will be tens because these values are infinity here. Okay, so 0 plus the weight of this edge is going to be smaller than this weight. Okay, so now what you do is you update. So the first updation is this vertex. So it gets updated to 3. So decrease key operation, I mean, not decrease key. So we don't have it in the queue. So we'll be inserting it into the queue with the key 3. Similarly, this will be inserted into the queue with the key 4. Okay. So this is the first iteration. So end of the first iteration, S is out of the queue. These two vertices are in the queue. Okay. So the next extract min would be on 3. Okay, so this red circle basically indicates the extract min vertex. Okay, so vertex with this, so not vertex with weight 3 will be the next extract min. Okay, now you look at the neighbors of 3, this and this. Okay, Now, is this edge tens here? 7 plus 3 is not smaller than 4, right? Since this edge is not tens, so we will not be processing this. Okay, so we'll only be processing this edge. So this edge, because here it was infinity, it's naturally tens. So 12 plus 3 is less than infinity. So we'll update it with 15. Okay, and put it in the queue. Now, what is the content of the queue? So content of the queue, so we have removed this vertex already, and we have removed this vertex, and we have included this vertex. So these two vertices are in the queue. Now extract min give us one with the least weight or least key, which is 4. So this vertex will be given to us next. Okay. So now you look at the out neighbors of this vertex, basically these two. Okay. Now see which of the edges is tens. So this edge, so 4 plus 5 less than 15. So this is tens. Okay. So we'll be updating. So updating to what? 9. And 4 plus 0. So okay. So this example, the weight is 0. Usually we'll assume weight as greater than 0, but it does not matter. 4 plus 0 is less than infinity. So update. Okay. So at the next iteration, so we'll have what are the elements in the queue? This vertex as well as this vertex. Okay. And this blue colored edges indicate the predecessor relation. So whenever we apply relax, so here we had applied relax. So predecessor of this vertex is S, predecessor of this vertex is S. Now predecessor of this vertex is this vertex with weight 3, and the predecessor of, so what did we do? Update here this vertex. So predecessor of this vertex will be this. So this basically represents the predecessor relation. Okay. Now the next iteration will be extracting 4 from the queue. Okay, so out of 4 and 9, these two are the ones which are present in the queue. We'll be extracting 4. So once you extract 4, this edge is tens. We'll be updating this. So this is done. Okay. The subsequent iterations really won't matter because you won't find any tens edge. Okay, so if you extract vertex with the label edge weight, distance 7, it's not key 7, it's not going to give us anything. Similarly, if you extract 9, it's not going to give us anything. So this will terminate here. Okay. So it's like, so the way you see it is, it's like a wave. You start the wave here, so you flood it, all out neighbors. So the moment out neighbors are into the queue, so you pick one, which is the least weighted one, and again flood out of it. Okay. So every time the processed vertex gets out of the queue, so this vertex is out of the queue now, this vertex is out of the queue here, this vertex is out of the queue. But you can see that in this example at least, the vertex is not re-entering the queue at any point of time. Okay, it goes out of the, once it goes out of the queue, it goes out for good. It never comes back. And at any point of time, you will be updating the blue edge or you're changing that blue edge if you found a better choice. Okay. So for example, here, this blue edge is thrown away in favor of this edge. So this was made blue. Okay. So this is basically the relax operation. So you're applying relax on this edge. Okay. So at the end of it, you will, the predecessor relationship. So these are this blue edges, like I said, they represent the predecessor relationship. So that gives us the shortest path tree. So what are the shortest paths? Shortest paths from this vertex to this vertex is this. This to this 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 is in fact this, not this. I mean, there is no edge. Yeah. And this to this is this. Okay. This is how Dijkstra works. Any question on the example?
Hello.
Yeah.
So we can see that once a vertex leaves the queue, it doesn't enter the queue. But how do we argue that formally?
Yeah, we are going to do it. So we'll, yeah. Okay, so we'll move on to proving the correctness. I hope the algorithm is clear to everyone. So at least based on this example, we saw that the vertex is never entering. Okay, so then the complexity is easy to compute because a vertex never enters. So number of iterations here is going to be n. That's the number of vertices. And the way, so if vertex is not repeating, then so this decrease key or insert operation, right? Together they will be applied at most once for each edge. Okay, because the edges are chosen outgoing as outgoing edges of a vertex. Okay, so for every vertex, every edge, it will be used for relaxation at most once. So the number of relax operations and hence the decrease key will be at most the number of edge times. So roughly the complexity is going to be size of E into, so decrease key, I'm assuming it will take log n, so log n plus size of V into log n. Okay, size of V is n, size of V m, so it's basically m plus n log n. Okay, that's going to be the complexity. Okay, so we'll write this precisely later. So now we'll move on to the proof of correctness of this algorithm. Okay. Okay, so we'll have a notation. So for I less than or equal to n, maybe, I mean, right at the moment we don't know if it is less than or equal to n. So for I 0 onwards, okay, 0, 1, etc., etc. So ui be the vertex obtained by ith call to extract min. Okay. Yeah, so that is u1 is the first call, which is the vertex s. Yeah, u2 is some neighbor of s, and so on. Okay. Now let's also have a notation. So let di be the value of distance. So distance is the value that we are storing. Initially distance of s is 0 and everybody else, every other vertex gets infinity. Okay. So distance, value of distance when it was extracted, let's denote it by di. Okay. So now we'll state two simple lemmas that kind of gives us time complexity, and then we'll prove the correctness of the algorithm as well. Okay. So the first lemma is the following. Okay, so in all these, we'll assume that there is no negative wait cycle. Okay. So the first statement is, if you look at the order in which vertices come out of the queue, okay, so we can argue that the distances, if at all, they increase. Or to be precise, for all I less than j, di, that is distance value for the vertex which is extracted at the ith iteration, is at most the distance of the vertex, distance value of the vertex which is extracted at the jth iteration. Okay. So remember that dj is the distance value at that point of time when it was being extracted from the queue. Similarly, di is that value with, of distance when it is extracted from the queue. Okay, so that is something we have to be careful about. So the proof is fairly simple. So what this says is, so let's maybe look at this example. Okay, so if you look at the distance values, what are the distance values of the extracted? So first is d1 is 0, d2 is 3, d3 is 4, d3 is 4, d4 is 4, d5 is 7. Okay, and then of course the next extracted will be 9. So d6 will be 9, 6 or 7, d6 7 will be 9. Okay, so if you see, the distances of the extracted elements keeps on increasing. That's exactly what the statement is trying to prove. Okay, so the distance keeps on increasing. Okay, so but why is this useful? So we'll prove it in a minute. Okay, so before proving it, so let's see why is this useful. So using this, we can immediately show that no vertex enters the queue twice, or no vertex is extracted from the queue twice. That means it enters the queue twice. Okay. Again, provided there is no negative wait cycle. Okay. So suppose G has no negative wait cycle, then every vertex V in V is extracted from queue at most once. That means it does not enter the queue twice. So we'll prove this first, so just to demonstrate the usefulness of the lemma I stated previously, and then I'll prove that lemma too. Okay. So we'll assume the lemma, previous lemma. Now suppose a vertex, there is some vertex V which is extracted more than once. Okay. Now let's have our indexing notation. Okay. So suppose it is extracted at the ith iteration as well as kth iteration. That is, suppose there are I less than k such that ui is equal to uk is equal to v. Okay. Now let's just understand. See, once you extract v at the ith iteration, it's out of the queue, right? Now to extract at the kth iteration, the same vertex, we'll have to enter it. It has to be reinserted into the queue, right? So then there must be a j which is in between I and k, such that v got reinserted into the queue soon after extracting uj. Okay. Uj is some vertex. We don't know what it is. Okay. Yeah. So just to make it pictorial, so say at the ith iteration, so this is v equal to ui. This was inserted into the queue. Now extracted from the queue, and again v equal to uk was extracted at the kth iteration. But at this point of time, v is not in the queue. After this, okay. So somewhere at jth iteration, v is added. But let's just try to understand how will it be added. So it will be added at the jth iteration. We must have applied a relaxation and then insert key. Okay. So at the jth iteration, there was, so what was the vertex coming out of the queue? Some uj. We don't know what it is. Okay. So but that uj must have cost. So that edge must have been tens, and hence it must have caused this vertex v to re-enter the queue, make it re-enter the queue. But what do I mean by saying uj ui must have been tens? So remember that ui is nothing but our v. Okay. So dj plus weight of, this is the other way around, I'm sorry. Okay. j2 ui. dj plus weight of uj to ui must be less than di. Okay. Now, so must be less than weight of di. So hence we have inserted vi, which is ui, which is v. Okay, so we must have reinserted the vertex v back into the queue. Now, when we extract it at kth iteration, the value is dk, right? The distance value. So if at all it would have gone down, because we only applied decrease key, right? So what we are guaranteed is the dk, that is the weight of or distance of v at the second time when we are extracting it from the queue, must be at most this value, that is dj plus weight of uj plus ui. Okay. Now by assumption, this is going to be less than di. So what we have is dk is less than di. Now where is the problem? I mean, okay, dk is less than di. What is the big deal?
Hello.
Yes.
Sir, can't we stop at the third step and argue that dj is less than di?
Yeah, but
And
dj, we don't know what that vertex is, right? Oh, so that's
in,
what you're saying. dj is less than di.
but I
Yeah,
is
that is also,
less than j. It is contradicting the previous lemma.
yeah, that is also good enough. Yes, you can stop there itself. Yeah, that's a good point. Yeah, that itself it's contradicting the previous lemma. Yes. Yeah, so see, there is only one catch. I mean, yeah, so you will apply relaxation only if it is strictly less than, right? Yes. So then it will contradict. So in either case, we have, I mean, yeah, so we already have a contradiction. Okay, so what was the previous lemma saying? So the distances of extracted elements will only increase, if at all. It might stay the same, but it won't decrease. Okay, so what we have is dj is greater or equal to di. Okay, so this already contradicts. Lemma as dj is greater or equal to di. Okay, so only way the previous lemma fails is if g has negative weight cycle. So if g has no negative weight cycle, this is not possible. Okay, so as a consequence of this lemma, what we have is it clear to everybody?
Hello, sir.
Yes. Yeah.
So from third step, we can, it's neglecting negative edges as well, because we can have that edge as negative and it's possible it can be less than di.
Yeah,
Not
that's
cycle.
true. That's true. Yeah, I mean, see, only way this can be contradicted is if you have negative weight cycle. So if there is no negative weight cycle, yeah, negative edge actually. Yeah. Yeah, that's true. Yeah. So if there is no negative weight, this contradicts lemma. But in any case, I mean, if you see this full argument, so what will end up is, so dk is less than or equal to this value. Okay, so hence dk is less than di. So even when the graph has negative weights, but no negative weight cycle, but then this will contradict the previous lemma. So hence the only possibility is g has a negative weight cycle, at least one. Okay, yeah, so you are right. I mean, if the weight is negative, then this is possible. If weights are non-negative.
Hello, sir. Can you explain
Yes.
the fourth step?
Yeah, so see, now when at the kth step, this vertex is being extracted, right? Now, if it is extracted, so it's guaranteed that this value is smaller than this value. It may not be equal because you might have applied decrease key again somewhere. Okay. See, when we reinserted the vertex v, its distance value was this, right? But when it is extracted, if at all, the value will be smaller than that because there could have been a decrease key in between. It's never going to increase. So that's why it may not be equal. So it could be equal if there was no decrease key, but potentially there could also be a decrease key. Okay.
Okay, sir.
Yeah, so this kind of takes care of negative weight edges, but no negative weight cycle. Okay, so if there is no negative weight cycle, both the statements are true. So what did we really prove? So we proved that if there is no negative weight cycle, then no vertex enters the queue twice, or no vertex is extracted from the queue twice. Okay, so every vertex is extracted from the queue at most once. So now we'll just prove the previous lemma, which is crucial in proving this statement. Okay, so we'll just simplify it. So all we do is, so we'll show that successive steps, the distance property will be maintained. That is, di is less than or equal to di plus 1. That would immediately give us the claim. Okay, so all I wanted was for all I less than j, di is less than or equal to dj. That is, distances never decrease. So when I say distance, I'm looking at the value or distance value of the vertex when it is removed from the queue. Okay, so if you consider it vertices in this order, it's never going to increase. That's all we want to argue. Okay. Yeah, so for arguing this, so there are two possibilities. I mean, based on whether the edge ui to ui plus 1 was present or not. Okay, so instead I'll just do it the way algorithm is working, okay, so there are two possibilities. Either ui plus 1 was in the queue when ui was extracted, or it was not. Okay, so these are the two possibilities that we will consider. So if ui plus 1 was present in the queue when ui was extracted, okay, again there are two possibilities. Either there was a decrease key or there was no decrease key. If there was no decrease key, then clearly di plus 1 is going to be greater or equal to di, because we got di through extract min when ui plus 1 also present in the queue. Okay, so that means weight of ui plus 1 will be at least as much as weight of ui. Now the other possibility is decrease key was performed. If the decrease key was performed, how did it I'm sorry. Yeah, so when I say decrease key was performed when I extracted ui. Okay, so when I extracted ui, I performed a decrease key. Okay, so here when ui was extracted, I might have performed decrease key on ui plus 1, because at the time of extraction the distance value for ui plus 1 will be greater or equal to that of ui, otherwise I would have extracted ui plus 1. Okay, so then it must be due to relax of ui plus 1. If a decrease key was performed because of this, then in that case di plus 1 is equal to di plus weight of ui plus ui comma ui plus 1. Okay, so again I'm kind of assuming here that yeah, there is no negative weight edge. Okay, so in this case I'm assuming that there is no negative weight edge, so di plus 1 is equal to di plus weight of ui comma ui plus 1. Okay, the second possibility is, yeah, so this kind of the statement holds negative weight edges. Okay, at least the proof I have given. So the second possibility is ui plus 1 was not present in the queue at all when ui was extracted. But then how did it appear in the queue? Because while processing ui, we might have inserted it. Again, going back to the algorithm, there would have been an insert of ui plus 1. Okay, but if you are inserting, what is the value of distance of ui plus 1? That will be basically distance of ui plus weight of ui plus 1. So again, di plus 1 will be greater or equal to. So if see, this could also be equal. Okay, I cannot write it as greater than, because distance, I mean, because weights could be 0 also. Okay, so yeah, including that possibility, this will be greater or equal to. So in either case, distance of the vertex which is removed after ui, immediately after ui, will be increasing or non-decreasing, to be precise. Okay, so in fact you can also see this two cases in the following sense. It is based on whether there is an edge between ui and ui plus 1 or not. This is ui, this is ui plus 1, this is ui plus 1. So if there is an edge, so no edge. If there is no edge, that means what? That is ui plus 1 was in the queue when ui was extracted. Therefore, di plus 1 is greater or equal to di. Okay, and since there is no edge, no update happened, right? So there is no update after extracting ui. Now there is an edge, so of some weight, let's say w is the weight. Okay, so then there are two possibilities. Okay, so one is ui plus 1 was present. Second possibility is ui plus 1 was not present. Okay. So if it was present, then so clearly at the point when ui was extracted, distance of ui plus 1 is greater than distance of ui, and even if you had updated it through decrease key, the distance value will be, so distance of vi plus 1 is at most distance of vi plus weight of ui plus 1. Sorry. Okay. So it's the same case, same scenario in the second case too. Distance of ui plus 1 will be equal to, in fact, equal to di plus weight of ui plus 1. Okay. So, sorry, not less or equal, it will be equal to. Okay. If decrease key was performed. So in either case, so see, when we extracted ui, distance of ui plus 1 as per the queue is greater than distance of ui. Now only possibility that it can go bad is you would have updated it, okay, through decrease key. But even if you do a decrease key, this is going to be the weight, which is greater than weight of di or distance of vi. Okay. Another possibility is ui plus 1 was not even present in the queue. In that case, its distance is going to be this. So in either way, we are beating it. Okay. So the same case analysis done in a slightly different way. Okay. So both are equivalent. I mean, it's essentially based on whether the edge is present or not. So only thing I have assumed here is no negative weight edges. Okay. Not negative weight cycles. Yeah, I'm not sure if you can relax this assumption to negative weight cycle. At least this argument will not go through. Okay. Yeah.
Then, sir, in the second lemma as well, it should be negative weight edges only.
Yeah,
Because we are
that's the
using the
problem.
first
Yeah,
lemma.
yeah, that is true. It's negative weight edges. Okay, so this also will work only for negative weight edges, not cycles. You're right. All of it. Yeah.
Hello,
Yeah.
sir. Can you tell me why we are assuming no negative weight edges in the previous algorithm? Previous
So
lemma, sorry.
yeah, otherwise the distance can go down, right? So when I do, so if this has negative, right, distance can go down. Di plus 1 can be greater, less than di. So that's a problem with the Dijkstra. So okay, it requires that there is no negative weight edges.
Okay.
So otherwise,
okay,
what will this argument will fail? Okay, so this, if this is negative, right? If this is -1, then I'll have di plus 1 is di minus 1, right? Di minus 1. That's a problem, right? This argument will not hold. Then you cannot, in the end, I mean, you cannot guarantee that the vertex will not reappear in the queue. So the running time bound of Dijkstra this way, it requires that, or at least this part of the argument, it requires that there is no negative weight edge, not negative weight cycle.
Hello, sir.
Yes.
If there is no negative weight cycle, it means that the vertex can reappear again if there are negative weight edges, but it will work correctly.
Yeah, so see, Dijkstra's algorithm will work, but the number of iterations will be more. So, okay, so we can argue it, but the number of iterations can go on as big as something like order of n square. Okay. We'll not really argue that. Yeah. So that's the problem there. Okay. So then we'll have to argue it slightly differently. I mean, how far can it decrease and so on. Okay. So that's the argument is bit not this neat. But in that case, I mean, there is Bellman-Ford which beats that version of Dijkstra. So Dijkstra is interesting only when there is no negative weight edge. And with this second lemma, it also tells, so the number of extract min operations is going to be at most n, okay? And hence, the number of decrease key is going to be at most m, right? Because you will be touching an edge and applying relax and hence decrease key corresponding to it at most once, because every vertex is processed at most once. So hence the running time is going to be m log n, okay? So yeah, so and with this assumption, no negative 8 edge, we can actually prove a running time bound of m log n, and that is a usual scenario where Dijkstra is applied. Okay, so when you have negative weight edge, then things, I mean, you can see this statement itself fails here. Okay, so this argument completely collapses. Okay, but you can still argue, but we can see in Bellman-Ford itself, if you even with the negative weight edges, if you run Dijkstra sufficiently many times, you will actually get the correct result. But it will be, the sufficiently many times will be really too much. Okay, so yeah. So the only thing that remains to prove, so this immediately gives us the time complexity. So by the previous lemmas, number of times extract min will be applied is n. Okay, so number of times decrease key or insert applied will be m. So therefore total complexity so order of m plus n times log n. So this is, we are assuming heap implementation of priority queues. Okay, so overall complexity of Dijkstra algorithm is order of m plus n log n using heaps. But if you use Fibonacci heaps, order of m plus n log n using Fibonacci heaps, which we didn't really discuss in detail. Okay, so Fibonacci heaps, you can do decrease key operation in order one time, insert as well as decrease key in order one time. Okay, so yeah, for this we have assumed that there is no negative weight edge. Okay, okay, so yeah, I'll take 2 more minutes, okay, just to prove the correctness. So see, all this basically tells us the time complexity. Okay, so this lemma 1 and lemma 2 combined, they give us the time complexity, that is time bound is this much, but now why these are the distance values? Okay, the
So,
actual distance, shortest distance. Yeah,
in heap implementation, why there is a factor of m into log n? I understand the n log n part.
because decrease key can take log n time, right? So decrease key will be applied in the worst case for each edge, right? You might apply relaxation for each edge in the worst case.
Okay, okay, sir.
Right? So that is why, yeah, m into log n. Okay, so now I'll just prove the final correctness by a simple inductive argument. Okay, so suppose, yeah, so again this should all be negative 8 edges. Okay, yeah, so suppose V has no negative weight edges, then after the termination of Dijkstra algorithm, distance V is the length of a shortest S to V path, and S etc. So starting from at the end V and then predecessor of V etc. ending at S is such a shortest path. Okay, so will argue that distance is the actual value of shortest S2V path. Okay, and then it will also follow that the path represented by the predecessor relation is also such a shortest path. Okay, so the way we argue is the following. So what we do is, so take any path, say V is some vertex, so this is an arbitrary vertex, so for every such V the statement will hold. So take any S2V path, let's take it as rho. Okay, so this is rho. So rho is this path. You start from S, I label it as V0, and at V I label it as Vk. Okay, now we look at prefixes of this path. Say rho I is a prefix, V0 to Vi. Okay, so V0 is S, remember, and Li be the weight of that path, that prefix. So what we'll argue is, by induction on I, we'll argue that distance of V is at most rho of I. Okay, so the distance computed by Dijkstra's algorithm is bounded by rho I. Okay, so that's what we are going to argue.
Hello.
So yeah,
Sir, what is rho I there?
rho I is the prefix of the path. So V0 to Vi. Again,
Like,
I mean, this
I didn't
equal to
understand that.
notation is bit. Sorry.
What do you mean by that prefix?
Yeah, so if the path is say V0 to Vk, I stop at the ith vertex Vi. That is a prefix.
Is it a number or is it a vertex?
What is a number? Rho I is a prefix path, V0 to Vi.
Because you're saying distance of V is less than or equal to rho I.
So yeah, so so distance of Vi we can say. Sorry, it should be Vi. Yeah, not V. So okay, so what you're saying is here, sorry, Li it should be, okay, not rho I. Is it clear?
Yes, sir.
Yeah. Okay. I'll take 1 more minute. Okay, so just in 1 minute I'll try to complete this. Okay. So the base case is I equal to 0. I is distance of S. Okay, that's straightforward. There is nothing to prove there. Okay, so all we prove is by induction hypothesis, distance of Vi is going to be less than or equal to Li. By induction hypothesis, what we have is distance of Vi minus 1 is at most the length of the path up to I minus 1, that is Li minus 1. Okay, so now let's just try to see. So when Vi minus 1 is extracted from the Q, so either the distance of Vi was less than or equal to distance of Vi minus 1 plus weight of Vi minus 1 comma Vi, that means no relaxation was applied, or distance of Vi was set to this number after relaxing Vi minus 1 Vi. So in either of the cases, so distance of Vi is at most distance of Vi minus 1 plus the weight of this edge Vi minus 1 to Vi. But by induction hypothesis, this is at most Li minus 1. Okay, so there is again a parenthesis missing. Okay, so but Li minus 1 plus weight of Vi minus 1 Vi is nothing but Li. So hence distance of Vi is at most Li. Okay, now we continue this way. I mean, if when I is equal to k, what we have is distance of Vk is at most Lk, that is length of this path. So what we have argued is, if you take any path from S to V, the distance computed as by the algorithm is at most length of this path, or in other words, distance of V will be equal to the shortest path. Okay, because distance is upper bounded by length of any S to V path. That's what this argument. Maybe I'll go in, because I'm doing it in haste now. I'll be doing it again in the next lecture. Now, one thing is I want you to think about, so how do you get that this is in fact a shortest path? I didn't really write the proof here, but the same proof immediately gives us, with the slight no modification, in fact, essentially the same argument also gives you that this is such a path. Okay. Yeah, so we'll continue in the next lecture. I'll redo this argument so that, I mean,